Hey guys, Miss Peterson here, and welcome to AP Chemistry Lecture 1-4, all about atomic structure. Today we're going to be talking about subatomic particles, protons, neutrons, electrons. We're going to be talking about the actual structure of the atom, talk about isotopes, and the percent abundance of different isotopes, and mass spectroscopy. If you're following along in your textbook, your Brown LeMay textbook, it is sections 2.3, the modern view of atomic structure, and 2.4, atomic weights. This is from AP Chem topic 1.5, atomic structure and electron configuration. So first, let's talk about the structure of an atom. Okay, how small is an atom, really? Highly recommend the TED Ed video for that. So basically, atoms are about on the order of an angstrom, okay? Now, an angstrom is a unit that we use in chemistry a lot to talk about the size of atoms, where 1 angstrom is 10 to the negative 10 meters, or 0.1 nanometer. To give you guys a little bit of a sense of how small that is, here is my meter stick. It has 100 centimeters, and then these little teeny tiny lines on it are the millimeters, and there's 1,000 of those on this 1 meter. Okay, now if you took one of these little spaces between the millimeter lines and divided that one by 1,000, you would have a nanometer. Okay, so one of these little areas, divide it by 1,000, so 1,000 lines in between there, get to nanometers. And now 0.1 nanometer is an angstrom. Okay, I also tend to use this in another form where I have 10. Oh, that is not the size I wanted. Where it is 10 to the 10th angstroms equals 1 meter. Okay, so a couple different ways you can convert that. Now, of that 1 to 5 angstroms, okay, a teeny part of it, on the order of 10 to the negative 4 angstrom, so that thousandth of a thousandth of a thousandth, okay, is the nucleus. Now, though the nucleus is super tiny, it is where 99.9% of the mass of the atom is. Okay? It contains protons, which from now on I will be abbreviating as P+, and neutrons, N. Okay? Now, these things that you might think, how do they keep all of those protons close together? They both have positive charges, and remember, like charges repel, but they're held together by the nuclear strong force, okay, which is one of the strongest forces in nature. Okay, it's one of the fundamental forces, and this power, just think, a nuclear bomb. When you break that nuclear strong force, it releases tons of energy. Now, the electron cloud, which is around the nucleus, is what determines the volume of the atom. Determines the volume of the atom. Okay? And it is a cloud of potential. And we'll talk about that more when we get to talk about orbitals. Now, if you're thinking about this and how these stay together, the nucleus has a positive charge, and the electron cloud has a negative charge. So they attract each other via electrostatic attraction, and that's what keeps the atom together. Okay, cool? Okay, so let's kind of get these numbers into concepts. The diameter of a US penny is 19 millimeters. The diameter of a silver atom is 2.88 angstroms. How many silver atoms could be arranged side by side in a straight line across a penny? Okay, so in order to compare these two diameters, we're going to need to have them in the same units. So I'm going to go ahead and convert the 19 millimeters to angstroms. So in order to do that, I start with 19 millimeters. Now, I could probably figure out how many millimeters are in an angstrom, but I know how many millimeters are in a meter, and I know how many angstroms are in a meter, so I'm just going to use those numbers. Okay? I know that there are 1,000 millimeters in 1 meter. Okay? And then I know that 1 angstrom is 10 to the negative 10 meters. Or you could use it this way. 10 to the 10th angstroms is 1 meter. Doesn't really matter which way you do it. I will go ahead and do it with the 1 meter is 10 to the 10th angstroms. Okay? I could go one step farther and figure out the number of silver atoms from here, but I'm just going to solve this out because I think it makes it a little bit more clear. So we have 19 times 10 to the 10th divided by 1,000. Okay, so the diameter of a US penny in angstroms is 1.9 times 10 to the 8th angstroms. Okay, so then we could take that number, divide it by 2.88 angstroms per silver atom, and we get 6.6 or 6.59. Keep it to, oh no, we only had 2 digits there, so we would want to say 6.6 times 10 to the 7th silver atoms. Could fit across a penny. Okay, you could have also done this by just adding one more step in the conversion factor here. There's 2.88 angstroms per silver atom, per 1 silver atom. And then that would have allowed you to skip right to that answer. Okay, 2.88 angstroms is 1 silver atom. Okay. Now, let's talk about those subatomic particles. That's the general structure of an atom. Let's zoom in and talk about protons, neutrons, and electrons. When we're talking about these, we'll often use the units AMU, or atomic mass units. How AMU is set is that 1 AMU is 1/12 the mass of a carbon atom, which is about 1.66 times 10 to the negative 27 kilograms. Okay, so you'll note that protons and neutrons are all about 1 AMU. Okay, it's not till you get out to that 1,000th place that they get off from 1. In most situations, you'll end up just using 1. Where electrons, note that they are on the order of 10 to the negative 4. So if a proton neutron is 1, the electron is 0.000, technically 0.0005. So much, much, much smaller, so much so that typically we consider their mass negligible when counting the mass of an atom. Couple different ways you'll see atomic symbols written. Okay, on the periodic table, the atomic number is often up top. The atomic weight is often down below. But if you're doing isotope notation, it's actually the opposite, where the number on the bottom is your atomic number, aka the number of protons. Okay, up here is the atomic mass, aka the number of protons plus the number of neutrons. And then sometimes there might be a number right there, and that represents the charge of the ion, aka the number of protons minus the number of electrons. And if it's not there, we always assume it's neutral. Okay, so always assume neutral atoms unless told otherwise. Okay? Okay. But that might bring up a question. If protons and neutrons both have a mass of about 1, how do we have atomic weights that aren't that close to whole numbers. That one is, but we have some like chlorine, which is 35.45. Why? And the answer to that is isotopes. Okay? If you have a bag of M&Ms, you ever get that random big M&M? Same happens with atoms. For example, carbon 12 is the most common, where carbon has 6 protons and 6 neutrons. However, there's also a pretty high proportion, not a high proportion, just higher than the other ones, okay, that is 6 protons and 8 neutrons, and some that are 6 protons and 7 neutrons. Now, they're not as common, but it does happen. And that's what we call an isotope. So isotopes are atoms with the same number of protons, but different, be consistent, number of neutrons. Okay, so they're the same atom. Remember, it's the protons that determine the identity of an atom. But if you have one carbon with a mass of 12 and one carbon with a mass of 14, or carbon 14, those atoms are isotopes of each other. And the mass that you see on the periodic table is an average, okay? It is the average mass of those atoms, okay? And because they show up in different amounts, it is what we call a weighted average. So, for example, in that carbon 12 one, if 99% of the carbon in the sample was carbon 12 and only 1% was carbon 13, we would multiply the percentages by the mass and then add them together to get our atomic weight. This is super similar to when you're in class and your teacher has different categories at different weights in your grade. So let's go ahead and do some examples of these things. Make sure you have your periodic table handy. First, we're going to look at the different notations and fill out this table. Okay, if we have strontium 90, that is strontium with a mass of 90. If I find strontium on the periodic table, it is number 38. Okay, so we would put strontium 90 would go on top. If we want to put the number on the bottom, often it is left off, so it's not incorrect to leave anything blank there. But it is atomic number 38. Okay, if it doesn't say anything about charge, assume it's neutral. So it has 38 protons and 38 electrons. And then to get the neutrons, it would be 90 minus 38, which is 42. I lied. It is 52. And this is why I don't do math in my head. Because it's Friday and my brain isn't functioning that well. Au, that's gold. With a mass of 197. It didn't tell us what its atomic number was, so we have to find it on our periodic table. It is 79. So it has 79 protons and 79 electrons. And then 197 minus 79 neutrons. So 118. Okay, now we have Ba, which is barium. Okay, barium is atomic number 56. So it has 56 protons. Again, protons are the identity. But this one has a charge of +2. Okay, that means it has 2 more protons than it does electrons. So only 54 electrons. And then its number of neutrons, 134 minus 56 to get 78. Okay, now we're looking over here, 82 protons, 82 electrons, mass of 126. Let's see, who is number 82 on the periodic table? It is lead. Okay, So this would be lead. It wouldn't be lead 126. Okay, you have to add the protons and neutrons together. So 126 plus 82 gives you 208. So 208 is the mass number for that isotope of lead. Okay, lead's chemical symbol is Pb. That doesn't look like a P. Pb. Fun fact, Pb comes from the Latin name for lead, which is plumbum. And if plumbum's not a really cool word, well, I think it's a really cool word. I like it. So 208 for lead. Now let's practice some of that weighted average stuff. So 3 isotopes of silicon occur in nature as represented in the table below. Based on the information, calculate the average atomic mass of silicon. Okay, so if we're just looking at this and kind of conceptualizing it, we see that most silicon is silicon 28. So our average atomic mass should probably be pretty close to 28, but a little bit higher because we have these heavier isotopes. So to calculate it, we're going to multiply the percent abundances. However, make sure they're in percent or decimal form. So we would multiply these together by those masses and then add up that to get the weighted average. So 0.9223 times 27.97693 gives me 25.8031. Okay. Now we have 28.97649 times 0.0468. Okay. 1.35610 and 0.0309 times 29.97377. Okay, and you get 0.92628. So then we add all of those together. And we get an average atomic mass of 28.085 or 0.86. Because our percentages only had 3 digits, I would probably want to round this and say 28.01 or 28.08. 28.08 is what is represented. Oh, it's 0.09. Oh, yep, 0.5. Is what is represented on the periodic table. So there is our weighted average. Okay. Another way that you could write this out, kind of in a formula way, that would be equal to 0.922, just to show you guys what we did there, times 27.97693 plus 0.0468 times 28.97649 plus 0.0309. Let me move this over. Times 29.97377. Okay. And that's how you do a weighted average. Let's try a more challenging problem. Okay. So naturally occurring chlorine is a mix of 35 chlorine, which has an atomic weight of 34.969, and 37 chlorine, which has a mass of 36.966 AMU. According to the periodic table, the atomic weight of chlorine is 35.453 AMU. What is the percent abundance of each isotope? Okay, so let's organize our information. Okay, we have 32 isotopes, one with a mass of 34.969, okay, and that is the chlorine 35. And then we have the chlorine 37 with an atomic mass of 36.966 AMU. Now, we know that the average is 35.453 AMU, okay? So, the question is, what is the percent abundance of each isotope? Now, because it doesn't say, we're going to assume that these are the only two isotopes there. So you might be thinking to yourself, wait, I have two unknowns. But how could you set it up so that you don't have two unknowns? Well, say the chlorine 35 is X percent. If these are the only two isotopes, okay, it says it's a mix of this and this, then this percent is going to be 100 minus X percent, okay? So that's how we can set up our formula and get those percentages. So here we go. We have 34.969 times some percentage plus 36.966 times, oops, not 100, I'm in decimal form, so 1 minus X percentage equals 35.453. And then it just becomes an algebra problem, okay? 34.969x plus 36.966 minus 36.966x equals 35.453. Combine like terms, so we have 34.969x minus 36.966x, okay? And I got a negative number, but that's fine. It'll go away. 1.997x equals 35.453 minus 36.966. Negative 1.513. So then divide them both off. And we get that X equals 0.7576, so 75. Now we'll get a little bit more precise because we had very precise numbers. 7576, okay? Or this X is 75.76%. So then this one would be 1 minus that, or 100 minus that, 24.24%. So chlorine 35 is 75.76% of the chlorine atoms, and chlorine 37 is 24.24%. Okay, cool? Okay, cool. Next, we're going to talk about, wait a minute, how did they even figure out that there are different isotopes of atoms? Because, like, it's not like we can look at them and weigh them individually or take a sample of chlorine and separate which ones are the heavy ones and which ones are the light ones. How does that happen? The answer is mass spectrometry. So, let me explain mass spectrometry. First, okay, well, if you're doing this with like a big compound, you could do it with big ones too, and you smash it into a little small bits, okay? But you have a sample and you ionize the sample, okay? That is called the ionization stage. Then it uses a series of magnets to control those ions and pass them through a detector. Now, because they have different masses, they're going to be affected at different speeds, okay? So, different masses curve by different amounts as they travel to the detector. Okay? And now they can actually control that and use it to separate them based on their mass differences. And they can go through that, and what they end up getting is these peaks of atoms hitting the detector. Okay? A lot of times what you'll see on them is what's called a mass to charge ratio. And because all of the atoms go through the same ionization process, they'll all have a similar charge. And this just allows us to take a sample and separate it by different masses. Okay? And you end up with a graph showing those different masses. When you have a higher peak, okay, that means you have more atoms of that isotope than the smaller peak. So this kind of gives you an idea of what a mass spectrum would look like. Because that charge is always going to be 1, this represents the masses. Okay, so I have a small peak at 10 and then a larger peak at 11. So the mass is going to be in between 10 and 11, but because the 11 peak is much stronger, it's going to be closer to 11. So if we wanted to figure out what this should say what element, not a compound, sorry for that typo, what element is represented by the mass spectrum. We just need to find who has a mass of about 11. Beryllium is 9, and that doesn't make sense. It couldn't be 9 because that's like a lot less than 11. It has to be in between 10 and 11. Carbon is 12, nothing above 12. So it must be boron, which has an atomic mass of 10.81 AMU. Okay, cool? Okay, cool. Now, you could also use this to find your average atomic mass. Okay? For example, this one gives the relative abundance of a bunch of different isotopes of zirconium. Okay? You have the mass numbers here and the percent abundance. So using that data, which again, these masses are just rounded to that nearest whole number, so not as precise as our previous examples, but let's go ahead and figure out that atomic mass. The way we're going to do that is we're going to take that mass, multiply it by the percent abundance, but in decimal form. So move that decimal over 2 places, and then add them all up. Okay, I'm going to do this all in my calculator. So follow along with me and make sure you guys can get the right answer. We have 90 times 0.515 plus 91 times 0.112 plus 92 times 0.171 plus 94 times 0.174 plus 96 times 0.028. And I get 91.32 AMU. Okay, which makes sense. If I look at this, most of it is that 90, so the peak is probably going to be somewhere in this area between 90 and 92. Okay, cool. Okay, cool. That's it for today.